So, hello everybody, I'm Peter Denning, your host here in the Harnessing AI series. Today, we're going to turn our attention to computer vision, is that right? This is one of the earlier topics in use of machine learning. When I was a professor at George Mason University a long time ago, we had some faculty there who were trying to solve the computer vision problem. So this was a big deal, trying to figure out if you could recognize people's faces in images. And they had all sorts of techniques to do this, and very limited success. And so over the years, as we've gained more knowledge of the algorithms and we've gained computing power, we're able to do much more powerful things in face recognition, image recognition now. Mathias Kolsch, who's speaking today, is an expert on this. He's been working on that for as long as I've known him. He came to NPS, about 12 years ago now, or something like that.
Longer, yeah.
And this was his initial area. He was affiliated with MOVES, he still is. Set up a vision lab in MOVES. A lot of students came, did thesis projects with him. They did some really cool stuff. And then he went away to industry for 3 years. He came back here and with a lot of industry experience, and continues to work on these vision problems. He's now the principal investigator of a project with the JAIC, the Joint Artificial Intelligence Center, developing educational materials for them in artificial intelligence. So this is who's going to talk to you today.
Thanks so much. Good afternoon. As Professor Denning said, Mathias Kolsch, and I will give you a bit of a micro and macro view of what is computer vision and how is it used and what does it do and also what does it not do. As one of the key takeaways, I hope you will gain from this the appreciation of this particular discipline and its impact that it had on artificial intelligence. I actually suggest that you're here because of computer vision. Not in an existential kind of way, but in terms of why there is such a renewed interest in artificial intelligence and why we have these recent advances in this field of artificial intelligence. Computer vision has been around since the 60s probably. It famously, well, not started with, but one of the big moments was when an undergrad was told to solve the computer vision problem during a summer internship. But that didn't quite pan out in 50 years or so. And artificial intelligence was closely tied to it. The hype from the 70s when we expected robots to walk amongst us quickly subsided, and realism said that this wasn't so easy. Computer vision, though, is in a way a poster child science, and it allowed progress in artificial intelligence to be made in a very measurable fashion and step-by-step fashion. And that helped kickstart the revolution in AI in a more recent decade. So let me first tell you a little bit what it is and how it works. Who can see that there's a wrist fracture there, or whether there is a wrist fracture? It's really tough, and it's a bit of a personal story too, because this isn't my x-ray. I had a wrist fracture too, and even the doctors didn't see it in the imagery. Had they had an AI system to support them, a computer vision system to support them, maybe they would have actually picked this out. So a computer vision system trained on fractures would actually highlight the region on the bone where there's a likely fracture. So if you present this to a radiologist, this particular example I think is quite easy to pick out, but there's much harder ones. And one important aspect of this is that neither the AI or computer vision system nor the human are perfect at this. The humans get about, I think, 80% sensitivity. So this is in 5 patients with a wrist fracture, they pick out 4 correctly. But if you combine that with a computer vision system, that improves to getting 9 out of 10 correct. So it's not so much that the computer vision in itself would be providing the answer here, but it's the combined vision, computer vision and human vision system that can solve these tasks much better. And this is a theme that I'll come back to at the very end, actually, of my lecture. It is, however, really also highlighting the importance of computer vision for some tasks that we might not always consider to be a computer vision realm immediately, because we have skilled experts in this. So what is computer vision here? It is basically an image as input to a computer algorithm and an answer as output. It does not produce another image as output. It produces some text as output, or a localization of where there might be a fraction in this image. It goes by other names, image understanding, or machine vision, or computational vision. And let me break down what it traditionally does. We have a sensing equipment, a camera, be it on a phone or a digital camera, or it can be actually sensing in a different radio spectrum. It can be sensing sonar data, for example. It can be sensing video data. It can be sensing LiDAR data. It can be sensing 360-degree video. So all of that is input to a computer vision algorithm. A computer vision algorithm then pre-processes this image, or it extracts what we call features, image features, from the image. They can be things as simple as little bright points in the image, if you want to, for example, build a star tracker. It can be red disks if you want to reduce the flash glare, the red eyes that you get from a flash from a camera. It can be looking for corners, edges in the image. It can be looking for straight lines if you're trying to follow roads or something. So these are all kinds of features that it could detect, or change or motion. It can be looking for a certain texture or an appearance of something. For example, face detection. It's a classic problem for computer vision. Faces actually look very similar. They usually are a little darker at the top, a little brighter here, then comes a little darker shadowed eye area, then there's a bright spot in the middle where the nose kind of reflects the light off, and then down below the chin it's generally dark. So very uniform face appearance actually across the board. And so these features are extracted. And from then on, we don't talk about the image anymore, but we talk about the features. For example, I found a edge or a corner or a bright disk at this location in the image. That would be one feature. And I transform the image into a representation in what we call a feature space. So that's represented here, and it's usually a very high dimensional space, dozens, hundreds, thousands of dimensions where these features are represented. So we have removed ourselves a little bit from the pixels or picture elements that the original image is made up of. Brightness information, it's brighter here, it's darker there. And instead we have to describe the image in a fashion that is more invariant to changes, for example, to specific brightness or to lighting direction. Does my face get lit from the right, from the left, from above, from below? Some features, some aspects will remain unchanged. So we're looking for these invariant descriptions of the content of the image. And that is then one of these points in this feature space. Once we're in this high dimensional feature space, we can then apply a typical classification algorithm. So that's machine learning, that is statistics, probabilistic descriptions of the data set, and then recognition of patterns that they found in that space. So the real core computer vision really traditionally happened here in the feature extraction. And we can solve with this classification then questions as to what am I seeing in this image? Is there AK-47 in this image, yes or no? Right? I don't get an image back, I get coordinates of a bounding box for this AK-47 back. That is an output of computer vision. Or I see a car parked in front of a house. Or I reconstruct from a bunch of 2D images a 3D object, in this case a bunny, or I count the number of people, or I can find out that somebody wrote Monterey, California on an envelope to be mailed on. So this is computer vision basically. And traditionally, a lot of work went into this step, that is the feature extraction, right? And for several decades, people tried to build better and better feature extractors. One of the key aspects of them, again, was this invariance to changes that we didn't care about. So if you didn't care about the overall image brightness, well, let's get rid of it. Let's not be distracted by it. Here is what probably dominated the feature extraction world for about a decade. After this was invented, the scale invariant feature transform, or SIFT detector, it was used everywhere. It was used for object recognition, and it's very good for that. For example, for recognizing whether a certain book cover is present in a scene, it's very good. It does an excellent job. You can imagine, for example, trying to detect the face here. Let's say, the nose is in the middle. What this would describe is the major directions of brightness changes. Again, so there's usually a fairly horizontal bar where the eyebrows are, and it gets dark underneath. So it would describe that there is a lot of horizontal stuff going on. The nose would be somewhat vertical. Down here, it would be a little rounded where the chin is. So it would describe that basically in a numeric fashion. This would be normalized for rotation, for scale, for brightness, and so on. The key being that I get about the same numbers that describe all the faces in the room, roughly the same faces, right? So I have this scale invariant feature transform, works really well. Well, again, this was laborious work for many years. People worked on this, and it was patented. It was very commercially successful, academically successful. And then about 2012, 13, 14, we finally had computing power that was actually getting better. Now, how did that work? We figured out, well, instead of us crafting this, we're thinking about, well, how could I describe this in this invariant fashion? We let the computer figure this out. We let the computer determine on a lot of training data what would be the best feature extraction. And really, even prior to this, there was a two-camp kind of science community. There was the camp that said, we need better feature descriptors. We need better algorithms to determine this. And there was the other camp that said, no, we don't. We need simple descriptors. We just need a ton of training data. We just need to learn this thing. And so they kind of came together, and that's when the neural networks that had been around, mind you, for also some 30, 40 years at that time, started really taking off. Who could explain to me what a deep neural network is? Have you all learned this? I see one head nod, not so much. So let me talk a little bit about what this is. A deep neural network consists of neurons, right? There's 1, 2, 3, 4 neurons here. They're organized in these layers. This is the input layer, and then there's several layers afterwards. The input layer is basically the image. So in this case, let's say there's a pixel here that corresponds with this neuron, there's a pixel here that corresponds to this, pixel here that corresponds to that. My classifier, or my deep neural network, is then supposed to learn what color the traffic light shows. Right? So you can imagine that this is bright here, then this neuron bleeps and says, me, whereas this one is not so loud, right? But it's not entirely quiet. You see a little bright spot here, so it has some noise in it too. Anyway, these produce an output. Let's call that output A, B, and C. The next layer then, this neuron up here, has weights. We call them x1, x2, x3. Each of these inputs from the previous layer get multiplied with those, they get summed up, and we apply a function, a thresholding function to this basically, that says, well, if the sum is above a certain value, then this recognizes something. So you can imagine that this neuron up there, for example, detects when the light's green. And there's another neuron then that does the same thing for a red light, for a yellow light, for black light or something like that. They're what's called fully connected. So every one of these input neurons speaks to every single one of these neurons in this first hidden layer. And then these hidden layers now respond in some fashion as well. They produce some output. That output is fed into the next hidden layer. And in this case, there's 2 hidden layers and 1 output layer. Finally, there's an output layer that says, yes, this traffic light is green or red or something else. So that is a neural network. We have 3 input neurons. This is what a fully connected network looks like for 8 input neurons and a small number of hidden neurons in between. So this is very powerful. This can learn a lot of functions. But the images that you take with your camera, they have many, many more pixels. So how would the neural network look like for, let's say, your 100 million pixel Samsung Galaxy Ultra or some other fancy phone camera, right? It would explode. It would be way too complicated to be tracked. And that's kind of where the key innovation comes in here. What computer vision contributed to these deep neural networks was then suddenly some structure, some learning efficiencies that allowed it to really both capitalize on the expressive nature or the expressive power of this, that it can represent so many different functions, but at the same time do so efficiently so that we can actually compute something in a deterministic or finite, small enough time that we could get to a result here.
So what is that deep neural network magic that needs to happen? Well, again, we learn these features that we can extract from the images that will help us provide these answers. We have these hundreds of millions of parameters. These parameters are that x1, x2, x3, and so on for each of the layers. And we have a bunch of training images. So how does this all work? If you remember something from regression or optimization theory, there's these over-constraint and under-constraint problems. An over-constraint problem is one where you only have, let's say, 2 equations, but you need to match this equation to 50 input values. So it doesn't work. You cannot find a single set of equations that match this. You will have to optimize. You find kind of the best compromise. Then we have these under-constraint optimization problems where we have more equations than we have samples or variables to fill these. So we have an infinite number of solutions to these under-constraint problems. And deep neural networks are heavily under-constrained. So we can find bazillions of solutions for those few training images that we have. What deep neural networks or what convolutional neural networks provide is mechanisms and shortcuts that allow us to still arrive at plausible functions that actually fill this. But we still often have to try multiple times. We have to experiment quite a bit with parameter tunings to come up with a good answer. But really the key here is that this laborious feature extraction that all relied on a few smart minds in the past now is done by a computer that will really find some sort of an optimal solution to this. So let me show you what these layers look like, what the neurons look like in these layers. What I'm showing you here is so there's an input image, and then there's a visualization of the neurons and their weights at multiple layers. So in the first layer, input layer, this is kind of what the neurons look like. They basically say, I respond strongly. This neuron here responds strongly if it finds a diagonal line that is dark in this direction. This neuron responds strongly when there's a little bit of green and a little bit of red next to each other, and so on. So you get a whole array of these neurons that look for these very basic features, and that's when they fire really heavily. Then at the next layer, these neurons are all connected to, well, a good amount at least of these neurons in the lower layer. And they respond now to more complex things. So you can see already in this next level up that it looks for round things, which is a much more complicated shape than a straight line. And then finally, in the highest level neurons here in our highest layer, we would then respond to these entire classes, a bicycle, a car, and so on. So that's kind of how they're built. Let's drill in a little bit more. Let me actually explain quickly what I mean with these spatial correlations, feature sharing, and so on. So spatial correlations means I need to make connections between different parts of the image. For example, if I have wheels on a bicycle, I want to make sure that they're not on top of each other. That would not be a bicycle. So these correlations, they're fairly global over the entire image. They're very hard to make. And that's where these deep neural networks, deep meaning multiple layers, many layers, come in to be very powerful. Because at the lowest layers, I'm only finding things like, yeah, there's a wheel, there's another wheel. But at higher layers, I have a more global view of this. I see connections between the wheels. Maybe I see part of the frame. Maybe I see a bit of the road underneath. And I can figure out the global location of these smaller parts. So that's where they're very powerful. They use what's called feature sharing. So they reuse something that we've learned somewhere else, right? These diagonal lines, they occur for many, many different aspects in the image. Let me show you a couple other examples. This is for recognizing digits. That was one of the very earliest deep neural networks that was successful around 2000. It was actually in commercial application for in the post office for sorting mail. And you can see how in the lowest layer there's just dots and lines. In the highest layer, you can really make out individual digits then, and what those are being recognized. Visualizing a little bit more, amplifying these learned features can actually result in these kind of cool little psychedelic images here. So basically, we provide some input, fairly random input, to the neural network, and then we just tell it, well, go back and forth in your layers, right? Recognize something, and then project it back down into an image, and recognize it again, project it back down into the image. This is kind of what it comes up with. So you can, with that, visualize what a neural network is actually looking for, what aspects it is thinks are valuable to some recognition, and it kind of looks pretty artistic. This is also an ongoing research area that is not just playful, but we'd like to understand what these neural networks do. They're a bit of a black box, and we are cracking it open. We're learning how it learns, and we're learning when it doesn't learn the thing we thought it would have learned. There are failure cases that you might have heard of when you can recognize, for example, foxes and dogs, but then you realize, oops, it's not actually looking at the fox, it's looking at the background image. So if I have a dog in the same context as a fox, like in snow or something, it thinks it's a fox, because you've trained mainly on images of foxes in snow. So with these kind of techniques, you can find out if it is learning the correct thing that you're interested in. Right. I started the lecture saying that computer vision catalyzed really the recent surge of artificial intelligence advances and improvements. And so let me tell you why that is. I mean, we have, it could have come from anywhere, but why computer vision? Well, these convolutional neural networks, they're special neural networks, special deep neural networks, because they use convolutions. Convolutions are these image processing filters that look like these edge detectors or these diagonal line detectors that I just showed you. That's what the convolution is. And again, these occur, these little subparts of the image, they occur all over the place, right? My dark eyebrow looks something like I don't know, something else on a car or on a bicycle, right? So these are shared features in a way. And there are these efficiency that allow me to train something that is more universally useful for all types of objects that I might recognize in image. And that constrains the search problem, and that constrains this 100 millions of parameters search space for this under-constrained optimization problem. So this is something that is not inherent in every discipline where I might want to learn something. Also, for any science, it's often good that you have increasingly difficult problems that you can progress the science on. That was definitely the case for computer vision, right? We started with optical character recognition on digits, 10 different classes, very simple. And now we're trying to recognize tens of thousands of different classes of all sorts of images, objects out in the wild. A much more difficult problem. And in between, we had face recognition, so we had conferences that were dedicated to face recognition, an entire conference dedicated to that, until there was a point when we thought, well, the performance gains are very, very incremental. We've pretty much solved face recognition. Let's look for a more difficult problem. And so this availability of increasingly difficult problems really helped progress the science along. A huge push forward came in about 2012 when large data sets became freely available, large labeled data sets. So not just a million images, but also a million labels that said, in this image, there's a face here, a car there, and so on. So these labels were very difficult to, or time-consuming to obtain. And that came together with a very close collaboration between industry and academia. So for a lot of computer vision research progress, you need access to these massive data sets. And the last but not least was a bit of a chicken and egg, or what it is now, it's a bit of a chicken and egg thing with GPU capabilities or training capabilities and the hardware therefore. But at first, GPUs were graphics processing units, right? They were sold to you in a graphics card that you added to the central processing unit, the CPU in your computer. So they were meant for games, but we used it for training neural networks because they exhibit a lot of the same characteristics, these training procedures, as do graphics rendering procedures. So we utilized those, but before too long, by about 2015, 2016, all of the GPUs for data centers were bought by not graphics researchers or gamers. There was a real shortage of GPUs because all the AI and deep learning researchers bought those. And now, what you see happening is that the AI processing drives the hardware industry. There are so many startups building hardware specific to deep neural networks, to both the training and of what's called the inference or the application of a trained model to doing then the recognition. All of the major companies, internet companies, Apple, Google, Amazon, Facebook, Samsung, they all have their own in-house chips now for doing AI deep neural networks. So basically, they can solve these equations that you need to solve for the neurons in these layers very, very quickly, very efficiently, power efficiently, time efficiently. And so now it's come, full circle. The AI that was kickstarted a little bit with this GPU availability is boosting the, now they're called AI accelerators, but basically they're still the same thing. So had there not been computer vision, we probably would not have seen the advances in deep neural networks, and those can now be applied to all sorts of problems, from financial data processing to signal processing, denoising of electromagnetic frequency spectrum signals, and cognitive radios, and I don't know, there's a bazillion of applications. Here's a few more applications in the image domain. What you see here is computer vision helps there tremendously in a mass estimation of growth in mammograms. It helps in lesion detection. It helps in airflow visualization inside the lungs. This is macular degeneration, where it points out where this is going on in the image. And plenty more images. So in the slide set, you can read up these applications. They're just a few years old, but still times have probably already, or current research has probably progressed beyond these. Self-driving cars I want to talk about very briefly. This is a concept image. You can't buy this one yet, however cool it looks. But we would not have self-driving cars without AI and computer vision in particular. I was very surprised back, it's probably 2014, 15 now, when I heard that the successes with the self-driving cars did not so much rely on GPS or LiDAR, 3D depth sensing. They all relied on computer vision to a very large degree. It was all 2D images that were processed very efficiently and very successfully to estimate where the car is, if there's something in the way or not. I think Tesla was the first company that came out with a chip that or a board that they built themselves dedicated to the task of the autonomous localization and driving. So they're building their own board now. They have a chip. Well, the board has 2 chips, I believe, or 4 chips. And there's 2 hardware neural networks on the board. It's a 12-core CPU. It's got a GPU. So very parallel processing to process all that data just coming in from all the many sensors that they have around the vehicle. But the other manufacturers have now also followed suit, and they are, if not building their own, they're contracting with big chip manufacturers to build them chips as well for this. Just a couple more slides here, 3 more slides. So current research in computer vision. Deep neural networks or convolutional neural networks don't solve all of the computer vision problems. There is still a very active community, so it's a thriving field. And I want to just point out a couple of problems that they're currently working on. One of them is action recognition in videos, as opposed to just 2D images, or more complicated scene recognition of the generic kind and the specific kind, not just the 100 most popular monuments that you see photographed many times, but much beyond that. 3D scene reconstruction, obviously for driving, also for drawing flying drones around. And this gets very complicated. So for example, if you have a drone that's about to fly into a tree, a foliage, or a power wire or something like that, you got to have really good high precision recognition of 3D objects and where they're located, and then you can navigate around those obstacles. But it really seems we have advanced very far into that realm, and we can do quite well with that now. I mentioned detection of many object classes, so more than 1,000. A very difficult problem is learning from just a few samples, right? If you have only a mugshot of a bad guy that you want to automatically detect afterwards when this person walks through a city camera or is about to board an aircraft or something like that, how do you train one of these networks on this single image? Usually they take thousands of images of a class that they can then recognize. How do you do it with few examples? Fine-grained object distinction, telling, for example, bird species apart, or finding out specific attributes of a car. What model is this? This Honda Odyssey. Is this the latest Honda Odyssey or the one that I got from a few years ago? So what is it? Another big one is synthetic image creation or synthetic data generation, from deep fakes to extrapolating a photo of a 2D person to a 3D model of that person. Very cool research going on. Higher level reasoning, figuring out what are these 2 people doing with each other. Are they wrangling? Are they having a fist fight? Are they exchanging a binder, a folder, or a floppy disk? What's a floppy disk? And then also of a lot of interest is how to operationalize computer vision, machine learning, and AI, because you see these great research papers and you see these startups having these fantastic computer vision algorithms for something. How do you build that into like a medical product? How do I really take this computer vision algorithm that detects the wrist fractures and present this to a radiologist and say, hey, no, I'm not trying to replace your job. I'm trying to make your job better. How do you build this really in? How do you work with an algorithm or a computer that is not right all the time? That's only right 85% of the time. Is it useful? Is it not useful? What about, for example, network intrusion detection? What if it's wrong 1% of the time? Is it a good system? I don't know. There's billions of packets flying through the network. If only 1% of those are flagged, that will overwhelm any network system administrator. So no good. How do you do this? How do you improve the algorithm once it's deployed? You train on one set of data. You train your computer vision algorithm out at 29 Palms or something and at training grounds. And then you take it to Afghanistan, well, no longer Afghanistan, somewhere else now, and suddenly the world looks different. Does it still work? How do I retrain it in the field? How does it work? Can I just take a couple of photos and stick it into the computer, maybe on a floppy disk, and it improves its algorithm? So I'll talk a little bit more about this in the next lecture when I talk about DevOps and DevSec AI Ops, or whatever you want to call it. But it's not a solved problem. This just summarizes what I talked about. Computer vision outperforms humans for more and more tasks. Computer vision catalyzes deep neural networks and the current resurgence in AI. Explainability, predictability, robustness are some issues we're still working on. One last note I want to make is, well, is this really AI? What is AI anyway? And I think other people have talked about this here. So it's a very difficult definition of what is artificial intelligence. But for the most part, actually what's going on is that we're really just making associations, right? We're learning association of a pattern of pixels with a certain class. It's not really that smart. The example is if I draw a sketch of a llama or something, an animal that my kids might have seen once, they can figure out that this is a llama. It's impossible to teach a computer that kind of stuff. So it's not that smart after all, but there's lots of research going on in that as well. A lot of it is, for example, causal reasoning, rather than just trying to figure out correlations, which can lead us to wrong conclusions. We want to figure out if there's a causal chain of events. I encourage you to look more into this. It's a really, really fun topic. Judeas Pearl is a researcher that has some really deep insights into that. Here's a quote also that brings me back to a point that I made earlier. A key aspect that is often overlooked is that expert knowledge, human expert knowledge, about the task to be solved can provide advantages that go beyond adding more layers to a convolutional neural network, right? So if you ever find yourself in a position to be program managing a computer vision project, know that there's a limit to improving the algorithm again and again and again and again. Involve the humans in this, because they're going to be the ultimate users, and more often than not, you get a subject matter expert actually working with those automated systems, computer vision systems. Right. I didn't talk about many aspects of computer vision, such as malicious input. I didn't talk about more of the robustness things. So this was really just an intro lecture for you. I hope this explained a little bit what this is and how it works. Maybe it gave you an appreciation for the field and the contributions that it's made to AI. If you're interested in more, shoot me an email or ask me questions now. So thank you very much.